As you can see from the title, what I'll be talking about today are two connected topics, but seemingly different to begin with. So first of all, we look at the problem of integral routing, meaning we're given a certain network, we're given certain pairs of origin destinations, and we would like to route cars in a centralized fashion from their corresponding origin to their corresponding destination. That's what I mean when I say optimal approximation for integral routing. That's one first problem. Then we consider a different problem, whereby we do not have direct control over each and every car route, but instead we have indirect ways of controlling the behavior. And in particular, we can think about congestion pricing or tollings, for example, as a way to influence their behavior to achieve better performances. So there are two different problems, and what I claim here is that we can, throughout a common approach, try to tackle both of these problems. Now, obviously, a first remark is important here. I'm using the word integral to distinguish myself from much of the work I've seen yesterday, meaning the case where there are continuous flows and we can split the flow of cars arbitrarily. Instead, in this case, the problems I'll be talking about are inherently challenging because they arise from integral distribution, meaning we cannot take a car, split the car in half, and send half a car on the right, and the other half of the car on the other. Now, I guess many of you are familiar with the motivation here, but let me quickly go through this. Congestion is soaring these days throughout the world, not only in Europe or Italy, not only congestion, but also the costs associated to congestion. So I'm thinking about both direct costs, for example, the number of hours that we spend on the network. And in the UK, this amounts to about 1% of the GDP cost, by simply calculating the number of hours that we are packed up in a queue times an average hourly rate. This amounts to 1%, whereby indirect costs, such as those arising from pollution, are also significantly large. In the UK, transportation alone is responsible for 27%, so more than a quarter of greenhouse gas. Now, as these problems are extremely challenging and daunting, there is a number of solutions that have been proposed to try and tackle these problems. So there's a portfolio of solutions. Naturally, we've already seen transitioning to electrification. There's also interest in trying to tightly connect public transportation with private transportation, so intermodality, for example, or multimodality. But those two areas I'm particularly concerned with in this talk are these two here. So autonomous mobility on demand, as well as congestion pricing. So I'd like to go in details first with autonomous mobility on demand, and then move to congestion pricing. So in autonomous mobility on demand, we assume we have control of a centralized fleet throughout the city. Let's imagine Israel cars belonging to a common fleet, which we can control as a central fleet. Now the goal here is that of routing the fleet or each and every car in this fleet from corresponding origins to corresponding destinations. And naturally, there are a number of questions one could ask. Typically, the routing is done in a way so as to minimize some form of cost. And a typical proxy for that cost is that of congestion, meaning we would like to minimize some form of aggregate congestion throughout the city by routing cars from origin to destination. That's the first type of problem, the centralized problem. Opposed to that, there's the problem of congestion pricing. So in this case, we no longer have control of each and every car, and instead we have indirect ways of influencing the behaviors. One such way is that of utilizing congestion pricing. The idea is that of imposing tolls on each and every different link throughout the city in a way so as to improve the performance. Now, this has been particularly high because New York is rolling out their own congestion pricing scheme, but also other cities in Europe and also in the UK have been doing the same. In particular, in the UK, or in London specifically, there has already been a congestion pricing scheme running for more than 10 years. Though this is a very simplistic scheme, whereby you draw a certain perimeter and all the cars who enter such perimeter would pay a fixed ticket, and all the cars not entering that perimeter would not pay. So instead, what we're after here is trying to design more refined, if you wish, congestion pricing schemes, as opposed to these blunt policies that I just talked a second ago. Again, here the goal is still that of incentivizing minimal congestion, but in an indirect fashion by imposing tolls. Now, these two might seem seemingly different problems, and I would like to highlight here what are the commonalities and what are the differences. So first of all, we have MOD routing, so centralized routing. The goal is that of minimizing congestion. And in this case, the problem is in a way simpler, if you wish, because we have complete control, direct control over each and every car route. On the other hand, here we have congestion pricing. Cars do not belong to the same fleet, and we assume they actually belong to self-interested users. The goal is again that of minimizing congestion, but we want to do so indirectly through the design of tolls, for example. This adds an inherent twist, an additional twist to the problem, in that, as I said, we do not have that. So natural questions arising here are the following. On the left side, the question is the following. How much performance can we extract from the system in polynomial time? Let me remind you here that we are looking at the integral case of the problem, which is typically a combinatorial problem. So we will see in a second empty-half. So if we cannot get an exact solution, then how close can we get to an optimal solution? That's a typical question that the person working on the side of the word here would be asking. On the other side of the word here, then there's a connected question. Well, what can we achieve if we don't even have centralized control? If we release this assumption of centralized control, can we achieve the same performance? Yes or no? And if no, how much gap is in there between what can be achieved here in polynomial time and what can be achieved here in polynomial? Now, as I said, both problems are extremely challenging because of the integral nature of the problem. If these were flow problems, then there would be a simple and very well-known solution for both. In particular, here, under standard assumption of non-decreasing and insect convexity of latency functions, one gets a convex program, which one can solve. We've seen the talk yesterday from Hardness, whereby here the typical solution is given by marginal cost pricing, for example. So overall, what is the problem that we are interested in? We are interested in minimizing total congestion in the case of integral routing, both in the case where we have full control or we don't have full control. And I claim that we have two important results to be discussed in the report. So first of all, we present a tight anti-hardness of approximation for the problem where we have complete control. In other words, we will prove that there exists no polynomial time algorithm that can provide an approximation to this problem here better than a certain factor law, which I will give in the talk. So essentially, we can't get any better than this law. We can obviously get it in terms of multiplicative approximation. This essentially sets the bar on what can be achieved by any possible algorithm, right? Then on the other hand, we look at the problem when we have indirect control. And we will show that carefully designed congestion pricing schemes produce an approximation, specifically a price of anarchy, that actually matches the anti-hardness result we achieved before. Now, as a result of that, since the equilibria I'm interested in particular correlated equilibria, can be computed in polynomial time, I actually have a polynomial time with optimal approximation that indirectly goes through the design of taxation matrices. So essentially, you see here how we tackle the problem in a sort of combined fashion. First of all, we set boundaries on what can be achieved by any possible algorithm. And then we are lucky enough to find algorithms that require indirect interventions and yet achieve that performance. Let's start, if this is clear, let me stop here for a second and see if the general structure of the talk is clear, if there are questions, both here and remotely, and then I'll start with more details on the two main examples. Okay. So let me recap for you what is the setup. We've seen this yesterday, but I just want to make sure that everyone is on board. So we're given a set of resources, which one could think of, for example, as the edges representing an underlying work transformation network. And we're given for every resource a latency function. Now, this latency function simply tells us how expensive it is, how costly it is to utilize that resource as a function of how many agents are currently covering that resource. We are given a set of agents, which are depicted here with these red cards, and each agent is given a set of feasible possible choices. This is a subset of the power set. In particular, in the specific case of routing problems, every agent is given an origin, is given a destination, which means that the feasible set, meaning the set of choices every agent has, contains all the possible feasible paths. Now, I don't account for loops here, so that in this case, for example, we have two paths connecting origin to destination. Once every agent decided on a certain feasible path, then that agent would incur a cost. And that cost would be nothing but the travel time from origin to destination, which is captured by summing the corresponding latencies over the path going from origin to destination. So, for example, if the right agent here was to take this route, this route, this route, this route, it would be summing the corresponding latency for this edge, latency for that edge, and so on and so forth. So this is nothing but a fancy way to talk about travel time from origin to destination. Now, the important point here is to then understand how do we quantify the performance of an allocation from a system perspective, from a societal perspective, meaning, say each and every agent now agreed on a path to take, how do we measure as society how good that overall behavior is? And to do that, I'll utilize the notion of system cost, which is nothing but the sum of each and every agent cost. This is typical in the literature. And you can think of this as the total travel time spent on the network. Meaning, for example, we think about the morning, everyone going from home to this room here. We think about the time each of us spent on the network. We sum this time as well. That's the actual total travel time, which I call here system cost. As I said, in the continuous case, this problem has been thoroughly studied, and obviously here I'm providing references only to control-like literature. There's obviously more than that, obviously in operations research, in mathematics, and in many other areas. Nevertheless, the integral problem is actually open, meaning that it is not known, it was not known what was the best approximation in terms of minimizing the system cost. So let me provide you with some of the most important literature results. So I'll denote with min SC the computational problem of minimizing the social cost. So I'll refer to min SC as the problem of let's find routes, integral routes that minimize the total time. So there are two well-known results. The first one is due to Myers and Schultz about 10 years ago, which essentially proved that the problem is NP-hard. Meaning, if we assume P is different from NP, then we can't get an exact solution in polynomial. Not only it's NP-hard, but it remains NP-hard, even if the latencies have very special structure, meaning the latencies are linear functions, in a very simplified setting, if you wish. This is what we know in terms of a hardness of the exact problem. If we then think about hardness of approximation, meaning how close can we get to the optimal solution, then there is only one result known to the best of my knowledge. This is due to Hardness, which essentially shows that in a very specific setting, so if we take latency functions to be polynomials of maximum degree, then we know that it's actually hard to approximate this problem here within a factor that depends in this way on the degree of the largest possible degree, with a coefficient beta here, which is not known. So essentially, this is, if you wish, an implicit anti-hardness result. It's not a concrete result. We don't know what beta looks like. It's an existential result in terms of there exists beta such that it's simply hard to do better than this. What is beta? We don't know. So if you want to think about it differently, this gives us an asymptotic behavior in terms of d, because beta is a constant, but we don't know what is the hardness result for a given. So overall, I'd like to argue that there is no tight computational lower bound, or more in general, no lower bound if you discount this case where beta is not. On the other hand, our result will completely settle this first question. So I would like to state the result in a simplified setting, but then I'll tell you in a second how this generalizes. That's our first main result, and it concerns the hardness of approximation. I look at a case where all latencies are identical. As I said to begin with, we'll get the more general results in a second. And I call these latencies B. So every edge is essentially identical as a certain latency, which I call. So then I claim the following. I claim that minimizing the social cost is actually hard to approximate within a factor that is explicitly defined by this expression. So first of all, let's make sure that this is actually well defined. So this is the latency here. So this function is a function of x at the denominator. And what we notice is that the numerator here is nothing but the expected value of the denominator, where the variable x is replaced by a Poisson random variable of mean equal to x, of parameter x. Okay, so this is a function of x, the whole ratio, right? And then I'm taking the worst case over the integral axis of this ratio here, and I call that number off. Naturally, that number depends on b, because b comes in here. So for different latencies, I'm going to get different numbers. So this might seem a little bit daunting to begin with. Let's just instantiate this in a very simple example to see that actually we do get complete bounds, not just expression we can't evaluate. So for example, if we replace a latency function here to be a linear latency function, so if we take v to be alpha times x, and then you compute this expression, well, this expression, especially the numerator, will turn out to be x squared plus x. So supremizing this expression is trivial, and one gets rho v equal to. So in other words, we're just instantiating this result. We learn that in the linear case, it's NP hard to approximate. Mean SC is NP hard to approximate within a factor better than. Obviously, this is just an instantiation. This result works in general, no matter what specific basis or specific latency function is. Now, it does naturally generalize to different latencies, meaning the case where these latencies, where the latency is resource dependent, so we get certain latency on one edge, certain latency on the other edge. And in particular, it generalizes in a very trivial way, if you wish, in that if you have multiple latencies, the NP hardness, the corresponding row will be the worst produced by each and every latency in isolation. So you essentially think about all your possible latencies, you look at the worst case for one, for the other, for the other, for the other, and you do the worst case over all of them. So perhaps quite interesting in the sense that oftentimes this problem here is studied in the case of polynomial latencies is that of looking at what this theorem tells us for polynomial congestion gains. So for the case of polynomial congestion gains, we see the case of linear congestion gains here, but I can state a more general example simply by instantiating here. So we claim that if latencies are polynomials of maximum degree, then we know what is the NP hardness boundary, and this NP hardness of approximation is given by the following number, which is very well known in combinatorics. This is the d plus first Bell number, where d is the largest degree that we have in our polynomial. So this can be easily be read on a table. If you just Google Bell number, you get a table of Bell number. There's also a recursive definition. All of this to say that this is easy to evaluate. It's known for all possible values of d. So for example, if we set d equal to 1, we over the two approximation, the two hardness that I had before. And for example, if we look at quadratic cost, then hardness of approximation would be 5, and so on and so forth. Is there any question on the statement of the theorem before I move on? Quick ideas on how to prove this.
Again, approximating with the factor 2, it's finding feasible solution is not more than
correct. So yes. Yes, Giacomo is asking what does it mean to have a two approximation. To clarify, we look at multiplicative approximations, meaning that if we can find an approximation with an approximation factor equal to 2, this means that the cost at that solution is less or equal than twice the cost at the other. So we pay a multiplicative factor. And in general, we pay a multiplicative factor of for a generic okay, so we are trying to prove NP hardness of approximation. That's the main idea. So how do we do that? Well, we must be starting from some NP hardness nodes. In particular, we start here from a problem which is thoroughly studied in the computer science literature, and it's called gap label. So the idea is to reduce a problem from gap label cover to congestion gain and induce this gap equal to rho v in order to prove the hardness that we care about. So what is, again, I'm going to present just some of the ideas here. If you're interested in the actual details on how the proof is carried out, then I'll give you the pointer manuscript at the end. So a gap label cover problem, gap label cover instance is defined as following. We're given a bipartite graph. In this very simple case, we have left nodes and right nodes here, and very simple functions. And we're given a palette of colors. So we're given a set of colors. In this case, again, it's a very simple setup. I'm given a red color and a blue color. And these colors I want to use to color the nodes. So maybe I want to color this node red, this node blue. I want to assign colors to nodes. Though there is a third important element, which is that of set of constraints. So these constraints tell me how I should be coloring the right node as a function of how I've chosen the color to be on the left node, if I want to satisfy that constraint. So for example, here, I hope you can see, if I color this node here in red, and I want to satisfy this constraint, it means I must be coloring the right node in blue. If I don't color the right node in blue, this constraint here is not satisfied. So there is one constraint per every edge. Similarly, if I color this node blue, then this constraint is telling me that I must be coloring again the right node, and so on and so forth. So informally, I'm given a set of constraints, a constraint per every edge, which tells me as a function of the left color, how the right color must be. Now, this problem was studied implicitly in this very famous paper from Fege, and more recently brought forward in a number of other works. The NP-hardness statement is the following, at the extremely informal in the statement. The statement goes as follows. It is NP-hard to distinguish between two following cases, which are referred to as yes and no. It is NP-hard to distinguish whether there exists coloring that satisfies all possible constraints. Meaning, you put colors here and all constraints are satisfied. That's the yes case. It's NP-hard to distinguish between the yes and the no case, where the no case is there exists no coloring that satisfies even an arbitrarily small fraction of the nodes. So no matter how you hook up your colors, you can't even satisfy an epsilon fraction of the nodes with where epsilon can be taken to be arbitrarily small. So essentially, it's a quite strong, if you wish, hardness statement in that it doesn't simply distinguish between the case where we can color and we can't color all of them, but it distinguishes the case where we can color perfectly satisfying all constraints and when we can't even satisfy a very small fraction of the constraints. So that's the NP-hardness problem we will reduce from. And on top of that, we need to construct congestion games by starting from this problem here. And we do that utilizing a gadget, which we call partitioning system. This was again implicitly defined in Fege in a much simpler sense. And the idea of this gadget is as follows. Now let's think for a second about congestion games. In congestion games, we are typically given a set of resources, right? And we are given a latency function for each and every resource. Right? Let's assume that these latency functions are identical. Again, think about the simplified statement I made a second. So a partitioning system is this square object here. So think about this as a matrix, whereby in each and every block of this matrix, there are resources. So essentially here there are certain resources which are part of this set. R1, R5, R27, R64. And they are arranged in a very special way, meaning in a way that satisfies two key properties. That is, if we think about the column as an agent, and an agent having to choose different possible allocations, being there also, then the following happens. If agents coordinate themselves and choose resources or blocks of resources that live on the very same row, then the cost they achieve is very low compared to the case when agents coordinate themselves but choose blocks that are scrambled, meaning such that there are no two blocks on the very same row. So what I'm claiming is that this object is constructed so that if we get a row, the social cost is low, but if we get a scrambled version whereby only one agent is present on the corresponding row, the cost is very high. So how high? Well, this is constructed specifically so that the ratio between these two quantities, meaning the cost of the row and the cost of the scrambled, the ratio of these two quantities equals the inapproximability result that we want to achieve. Now, why would this item be of interest, and why are we looking at specifically constructing the item in this fashion? Well, we are doing so because what we will be doing in the proof is we will be starting from an instance of that table cover. We will utilize this gadget to construct a congestion game, and that congestion game will be such that if we are in a yes instance or if we are in a no instance of the original problem, we are inducing exactly this gap here in the social cost. Which means that if we were able to approximate the social cost to an approximation better than rho v, we would be able to distinguish between a yes and a no case of an NP-hardness, which is clear. Okay, I'll stop again here for a second and see if there is any question.
What kind of graph do you need? The graph is very simple. So how is it still power or what is the mean? How is it? What is the complexity of the graph? How does the complexity of the graph affect?
So Yes, let me clarify. There are two different graphs here, perhaps at play. One graph is this direct graph here, which comes from the definition of from an instance of gap label cover, and this is disconnected in a way to the graph that arises then in the corresponding congestion we construct. So these are relatively simple graphs in a way, but then the resulting congestion games that arise from this and piling up this together with that are rather complicated graphs. So in a way, I don't have a simple answer in telling you how does the complexity of the resulting congestion game graph impacts the complexity of the actual value. Does that make sense?
So the question I can do, if you look at the, if I fix the congestion graph, the routing graph, for certain classes, the hardness result doesn't. So your statement is for temporal.
Correct. So this is a worst case statement, meaning
Worst case,
you can construct an instance of congestion game that is bad. This is what this is saying. How bad? Well, wrongly bad in terms of approximation. It doesn't mean that if you give me a congestion game that would be hard to find an optimal solution with a factor of small.
no, it's,
Okay, the second result, as I said, so let me first start. The first result is about what can be achieved in polynomial time, no matter how much control we have over the agents, and this is what can be achieved in the worst case. The second result is about what can we achieve if we only have indirect control. It turns out we can actually match what could not be achieved. Again, the setting is as the one we've seen before. The only difference is that now agents do not belong to a centralized operator, so we can't control the behavior centrally. So we assume that each and every of these agents is self-interested, as for example we've seen yesterday. We think about a game theoretic setting, and we think about the case where agents are interested in minimizing their travel time from origin. We want to improve the performance of resulting equilibria, and so we measure the performance of such equilibria by looking at what is commonly known as the price of anarchy in the literature. So the price of anarchy represents the ratio between the system cost at the worst possible equilibrium and the system cost at the optimal allocation. Now notice that one could think about the price of anarchy simply as the approximation ratio of one specific algorithm, whereby the algorithm simply computes an equilibrium allocation. So then we think about this as the approximation ratio of that corresponding algorithm. It's nothing but the ratio between the system cost at that allocation and the system cost at it. So the goal here is that of introducing congestion pricing schemes which are tolls. So we introduce a toll in each and every link, each and every resource, which is potentially congestion dependent. It depends on how many agents are currently utilizing that resource. This is what this notation here means. The goal is that of trying to improve, to introduce this toll so that its efficiency decreases and decreases as maximum. So, as I was mentioning before, I would like to connect the price of anarchy with the approximation factor of a specific algorithm. In particular, let me notice that the price of anarchy measures the equilibrium quantity, but if we have an algorithm that can easily converge to the equilibrium, easily meaning in polynomial time, then that algorithm inherits an approximation ratio equals the price of anarchy. That's a rather straightforward. Right? And in fact, equilibria can be computed in polynomial time, not all the equilibria, let me clarify. For pure Nash equilibria and mixed Nash equilibria, this is not believed to be the case. They belong to certain complexity classes which have certain names, PPAD, for example, PLS. They are thought not to belong to P, but the question is not settled. But more generally, for correlated equilibria and coarse correlated equilibria, we do have positive results, which tells us that it is actually possible to compute these equilibria in polynomial in the size of the original. And for example, one commonly known result is that from Paccagnan garden. It's called the algorithm is called ellipsoid best hope, and then there's a number of variations of this. For example, an interesting one from Xinjiang later now. So as a result, the main point that I want to convey here is the following: we have a polytime algorithm with approximation ratio equal the price of one, because these equilibria can be computed.
Polynomial number of resources.
Polynomial in the full description of the original problem. So yes, definitely polynomial in the number of resources and in everything else. Yes, yes, yes. Number of links, number of layers, polynomial in that code.
Not in the number of paths.
Not in the number of correct, but correct. I'll get to that. It was an interesting conversation that went on yesterday. Yes. Not in the number of paths, but there will be ways of doing this also when there are exponentially many paths. I'll get to that perhaps if I don't. Please stop. Okay, so there's been a lot of work in the literature in trying to improve the price of anarchy. Why? So for two reasons. First of all, because we want to improve the performance of strategic behavior. And second, because then we can get interesting polynomial time results, right? So there's been a lot of work. This is a very limited list of results. And the work has essentially spanned 2 or 3 directions. One being naturally congestion pricing, one being information provision, meaning what if I were to be a central planner and to design to propose carefully designed information to the players, can I steer their behavior to better performances? And the third one is that of stacker-based strategies, whereby we assume we have control over a small fraction of the players, say an epsilon fraction. Can we route this space in such a way so that the corresponding following players would then give rise to an interesting behavior, interesting meaning with the system. And this is, as I said, a non-exhaustive list. Our work specifically is concerned with the design of those with one of these specific directions. But no matter which of these directions you look at, there is no matching approximation, meaning researchers have been able to improve over the untold price of anarchy over the price of anarchy with the original problem, but the known results do not match the approximability result I presented. On the other hand, I claim that our result does so, and it's the first one. I state the theorem in a very simplified setup, right? Then we can look at, I can comment on how this generalizes to the more general. So again, we look at selfish routing, integral selfish routing. We assume that all latencies are identical, so all resource costs are identical for ease of exposition here. And we assume that these are positive functions, non-decreasing function, and semi-complex. So semi-complex here simply means that x times b of x is a complex function. I claim that no matter what epsilon will give me, no matter how small we give this epsilon, I can design congestion pricing mechanisms in polynomial time such that the corresponding price of anarchy of correlated equilibria, for example, is upper bounded by the inapproximability factor I gave you a second ago, plus epsilon. And we can make this epsilon vanishingly small. So essentially this says there is an efficient way to design taxes, and this efficient way gets us exactly to the inapproximability result that we have 4 plus epsilon. So obviously, well, not obviously, the result extends with a little bit of work to the case of general latency function. So to the case where a latency is dependent on the resource, it's not common to all resources. And perhaps more interesting than this theorem, or equally interesting, is the following corollary, which is trivial observation as a consequence of what I told you a second ago, meaning that since there are taxes that gives us a price of anarchy of rho b plus epsilon, these taxes can be computed in polynomial time, and an equilibrium can be computed in polynomial time. We have a polynomial time to compute an equilibrium with optimal approximation. So the algorithm goes as follows. Here is your instance of congestion game. Compute your tax, that can be done in polynomial time. Compute your equilibrium, that can be done in polynomial time, and that corresponding allocation here achieves a performance that is the one in approximability result plus epsilon. Questions here? Sorry?
What are those taxes?
Yeah, exactly. I'll answer the question. I'll answer the question in the next slide. So how do we construct those taxes? So what we do is that we look at a slightly modified version of the original problem. So in the original problem, the system cost can be written in this following compact form by simply summing over the resources. Right? So you see the sum over the resources of xl of x, if you wish, or if we think about this notation here as representing the number of agents of a resource, this is what the system cost looks like. I'll be looking then at a slight modification of this, whereby I replace this expression here with the corresponding Poisson expected value. This is reminiscent of what we see in a second, right? So I'm going to define a different function, which I call social cost p standing for Poisson, where I replace this expression with the corresponding expected value, where now p is Poisson unknown variable with the parameter, the number of agents of that resource. Then the recipe to compute taxes is the following. First, I solve the continuous relaxation of the problem. That is, I solve the problem of, let's find flows now, no longer integral solution. Let's find flows from origin to destination, where I want to minimize the cost. But the cost I want to minimize is not the original social cost, it's a modified version of the social cost. This can be done in polynomial time. It's a convex optimization problem, which seems like the times. So let me call V star the solution of this problem. V if this is strongly convex, A solution if it is not strongly convex. Then using the solution of this modified problem, I'm going to be constructing taxes. How do I construct taxes? I construct taxes according to an expression which I'm not shading here in the general setting, but which you can find in the paper. So essentially, this tells us that once we know the solution of this problem, then we're going to plug the solution here in some general expression, and we're going to be given corresponding taxes. I'll instantiate this in a second for the case of linear latency functions, so then you get an idea on how this f looks like in there, but then there's a general expression. Okay, then the job is done, right? Because we simply need to compute an equilibrium of the game with these corresponding taxes, and this equilibrium is guaranteed to give an approximation that we design. So let's look at the case of linear latency functions, so as to make clear what all this recipe looks like. So in the case of linear latency functions, computing this expression is trivial. We've seen before, it was x squared plus x, if you remember. So this is what I have here. So what I have to do now is that I need to solve a flow problem whereby I'm minimizing the cost from origin to destination. This is a complex function. One can prove in general that this is always a constant as long as L is constant. So this is something that can be done efficiently. We get a solution, and I'm going to call V star the solution. And then in the case of latency function, the actual tolls take the following very simplified setting. So it's the original latency function, like AR times X, plus something else, while this something else depends on the solution of the computation problem. And this in particular, alpha, so the same coefficient times the solution of this problem. Now, this is just to give you an idea of what happens in the case of linear latency function, but there is a general expression for f, and I can talk about that if anyone has questions at the end. So this more or less concludes the two core topics, the two core results that I wanted to present here. Let me just summarize what we've seen. So we look at the case of centralized routing, where the goal is to route a field to minimize congestion in the integral case. So in this case, we ask the question of what can be achieved in polynomial time, and we've actually been able to answer the question on both sides, meaning we've been able to answer what can't be achieved, but also what can be achieved. On the other hand, here we look at the case where we have indirect control over the cars. We've been able to show that even if we have indirect control, we can achieve the same performance that we could have achieved if we had complete control over the entire population of cars by carefully designing these taxes in polynomial time. So I'd like to present a few remarks and then conclude. First of all, I think it's quite interesting for me that if we think about competitive decision making, meaning competitive players, and we introduce a very simple mechanism such as that of taxes, we actually achieve the same performance of the best centralized solution. Maybe maybe someone would say this is expected because in the continuous version of the problem, by utilizing, for example, marginal cost tolls, we can achieve the same performance. But I would say a priori in the integral case, the results are typically quite different. So I would have not expected this to be the case. It's also surprising that a simple mechanism such as that of taxes allows us to get taxes. Maybe taxes, one would have expected that maybe taxes weren't enough. And why am I saying this? Because taxes do constrain us quite significantly of ways in which we can modify the corresponding problem. In that taxes are agent agnostic. They don't depend on the label of the agent, don't depend on which specific agent is traveling on that edge. They are just common to all possible agents. So I would have expected that the agent-specific taxes maybe could have been able to achieve this result, but it was interesting to me to see that these taxes actually don't need to be agent-specific. Now, one could argue that the result I presented here requires the solution of a centralized optimization problem, and I do agree with them. That's what I said a second ago. Nevertheless, at the price of a small approximation factor, one can actually compute taxes purely in a local way, meaning without requiring any solution of any centralized problem. So if you wish, This would be the parallel of marginal cost tools, that marginal cost tools only require information on a specific link and they don't require any solution of a centralized problem. So it turns out you can do the same in the case of integral routing, and you use a little bit of approximation, but very little. So for example, in this work, we provide a general solution in terms of optimal taxes that only use local information. And for example, for a fine congestion game, you'll be comparing a 2.012, which is what you get if you only use local information, with a 2, which is what you get if you use complete information. Finally, we are currently running simulations in terms of understanding what is the real world behavior, and that what I said thus far applies to the worst case instance, right? So what happens to a real world instance? This is something we are currently playing with to understand whether the design inspired by worst case instances actually carry over in terms of performances of the real world instances. Having said so, I'd like to conclude and perhaps just summarize one of the core ideas behind the work, one of the core takeaways. So I'd like to say that judiciously designed taxes, meaning carefully designed taxes, can be actually computed in polynomial time and do achieve the same performance of what could be achieved if we had centralized dictatorial control over each one. Now, the results I talked about can be found in these two papers. The first one here contains the actual results I talked about today. While if you're interested in the local version of the problem, meaning local taxes, then you can find the results. I'd like to thank you for the attention, and I'm more than happy to discuss and